at the medical center Texas Medical Center came up to me, and he wanted to process a large number of data files. Now, in this particular space, which is cancer genomics, the file type is called a BAM. Ranges from 10 to 500 gigabytes in size. And there's a place called CG Hub, Cancer Genomics Hub, where all this stuff is stored. And he had identified a set of cases that he cared about. So these are the samples I care about. But here was the problem. One sample could give rise to multiple BAMs. Sometimes that's because two completely different experiments were done with that sample. And so different experiment types. And so you wanted both data sets. Other times, it was an update to a previous version of a file. And you only wanted one of those data sets. And so that was the complexity. It's like, given thousands and thousands of files, how do I pick out which ones we would need to extract and process and deliver to this guy? Because he wanted a subset of the data contained within each file. So this is the general problem of how do I filter and then deduplicate a set of records. And it's not big data. I mean, this is a problem space that can easily fit in a single computer's memory, because I'm not tracking the contents of these files. I'm just tracking the metadata about the files. What is the sample? When was this file created? What was the type of file that this represents? So the sample, the file type, date creation, you could think of those as being three different things, as well as other bits of metadata, like what is the actual unique identifier for the corresponding file that we would want to fetch if we like that record. And so the whole thing could slurp into memory, but it's too big for me to do in my head. You know, I cannot, as a matter of practicality and efficiency, load this up in a spreadsheet and make sense of it all, because the rules for deduplicating were actually quite complex. There were multiple criteria that would be sufficient for me to consider something to be a duplicate, and multiple criteria by which I would resolve a duplicate. Because in the history of this project, the Cancer Genome Atlas, there had been changes to the versions of reference genomes. And you don't really have to care too much about what a reference genome is, but it's gone through multiple versions. So if I had two files from the same sample and the same experiment type and were different reference genomes, forget the dates. I want the one with the later version of the reference genome. So there's explicit versioning as well as date information that I'm going to use to resolve duplicates. I've got sample name and experiment type sort of information in order to find duplicates. Another criteria is if for the same sample and same type of experiment, it's still not a duplicate if two different universities did the experiment, because that would be two replicates of the same thing, and I want both. So now it's sample type, sample, the type of the experiment, the university that did the experiment. And if I see the same values for all three criteria, then it's a duplicate. Then that means that somebody uploaded an update of a previous file. So I got to get this straight. All right. Got a question? Yes?
So if you find these three duplicates, you just say one.
Right. When there's a duplicate, when a true duplicate occurs, and I detect that a true duplicate has occurred based on seeing some set of columns that have exactly the same value, then I have to resolve that duplicate in some way.
And that's what you're referring to as deduplicating.
Yes. So deduplicating is I have to detect duplicates, and I have to resolve duplicates. So here's my plan. I am going to express the problem as a table, because it naturally was a table of rows and columns. And I divide those columns into three groups. One group of columns is the columns that I want to be unique. So when I'm done, in my final filtered table, I will never want to see a duplicate value of this combination of 3 columns, say. And depending on your problem space, it might be 1 column, it might be 2 columns, 3 columns, 7 columns, whatever. There'll be some set of columns that you say there should never be a duplicate combination of values in this set of columns. That set of columns should form a key. The next set of columns in your table is the set of columns that if you had a duplicate, you would use to resolve that duplicate. And so in the simplest case, that just might be a date modified column. But so there's always like the very simple case. If I only had 1 column that was like the key column, and I had 1 column that was the date modified column, then it'd be very simple. Whenever I see 2 values for ID, I'm going to pick the one with the latest date modified and be done with it. But we're generalizing that. Instead of a single ID, there are several things that are forming my key. Instead of a date modified, there are several things that are going together that I'm going to use to resolve duplicates. The third set of columns in your table is the set of columns that, although very important, they are just along for the ride when it comes to deduplicating. This could be, for instance, the column that is the exact identifier of the file in question or the record in question. You want to preserve that information, but say the MD5 checksum of your data file is clearly not something that you're using either to detect or resolve a duplicate, but it's very important. Let me show you what this data actually looks like. So here's the corresponding data. We have a participant, which is an actual human being that donated a blood sample and also a tumor sample. This aliquot barcode uniquely identifies either a blood sample or a tumor sample. Here's an UUID for the aliquot that is just restating, but in a more computer-friendly, the same information that was in the aliquot barcode. So there's 1-to-1 between this column and that column. Disease abbreviation, in this case, that was a colon adenocarcinoma. Who cares? This, you don't care about that, but we actually do care a lot. Center name, that is the university that did the experiment and generated the data. This is the unique identifier of the resulting data set that we either want to download or want to ignore because we say, oh, that's either a duplicate or it's not in the interesting set of data that we were looking for in the first place. Then we start looking at some columns, a number of columns to analysis date, published date. Okay, that's, I don't think you're not really going to care about that. Library strategy was denoting the type of experiment that was done, as was platform. So this was the type of instrument that was used. This was the type of experiment that was done. This is the version of the reference genome that was used when analyzing the data. I told you that there was this versioning thing that happened. And you could have 2 data files that were the same everything, but it was just reanalyzed using a different version of your reference. And so you'd want to keep the one with the later version, but look at these things. They're a mess. We're going to have to do something about this column and translate it into something sensible if we're going to use that to help us know which is older, badder, which is newer, better. Then there's the file name, checksum, file size. So there you go. So this is an example of a column that's just along for the ride. Very important column. It's not used to either detect or resolve a duplicate. Likewise, the checksum. And the analysis UUID, which uniquely identifies that file name. So that's the analysis UUID is going to be 1-to-1 with the file. Well, not quite 1-to-1 with the file. You could have 2 data files with the same name but different analysis UUIDs, and CG Hub will take care of that for you, and you don't worry about it. Yeah, because people could accidentally have 2 files with the same name. But this is the most important column that's along for the ride. It doesn't help me resolve or detect duplicates, but this is actually the critical output that I'm going to want. Now, in your problem space, in my space, I was dealing with metadata, data about these files. And I was trying to select which of these files do I want to process and extract for further processing so this guy could study, I think it was mutations in the TP53 gene or something like that. In your problem space, your table might be the data itself. It just depends. I mean, there might not be a second level to this. I mean, where I have analysis UUID, and that's one column, you might have 20 columns that are physical measurements that were being made of oil wells or who knows what. It depends on your problem space. Okay, so my plan for implementing this in Python is I'm going to use a dictionary. I'm going to use tuples, and I'm going to use lists. So the major Python data types. And the idea is that the key, the composite key, the columns that I say, these columns should be unique if I ever see two records with the same values, that's a duplicate I need to resolve. I'm going to store that in a tuple. That tuple will be the key of a dictionary. The value of the dictionary will be the list of records that matched that tuple, that had those values. So if I process all of my data and get to the end, and I look at one of those lists, if I've got more than one element in a list, that means I've got a duplicate I need to resolve. How do I resolve that duplicate? Well, the way to resolve it is I need to take the list and sort it based on some sorting function that's going to define my criteria. My sorting function will address issues like the fact that this reference doesn't even make sense. You know, these strings will have to map over to something simple and sortable or numeric so that it will sort. My sorting function will give me a mechanism to take this list of records and sort them so that I take either the first or last element of the list, and that will be my one answer, my deduplication. Now, there are two paradigms for tackling a problem like this. You could either start with a hello world program and start mutating that program over and over again until finally, this many generations down, you've got a script that was doing the whole thing. But I'm going to use a different paradigm to feel my way through using IPython Notebook. So if you don't know IPython Notebook, if you're not using it at all, you are doing it wrong. The notebook interface of IPython is something that every Python programmer should be using some occasionally, and some more often than others. This is where you go if you have a problem and you do not directly know the answer, if you're experimenting with a new library. There are a number of uses for this. I'm not going to go into how to get that installed. You can just go here and find out. It does come pre-installed in a number of scientific Python distributions, so both Anaconda by Continuum Analytics and Canopy by Nthought will bundle IPython, so you could just do a stock standard installer and have it ready to go. In any event, the way you do this is you would cd into the directory where you've got data and run IPython Notebook. When you do that, your terminal turns into a web server that's serving to local host. On most systems, your default browser would start up and show you the list of IPython Notebook files in that directory. So the one I'm going to focus on here is deduplicating. And this part should look fairly straightforward. This is just me opening the file and reading the whole thing in. So in this particular case, I'm doing a very quick and dirty parse of a tab delimited file where I can assume that there are no blanks in my tab delimited file. So I was able to, I didn't have to bother with the CSV module or anything fancy. I just said for every line I read, I'm going to strip off the new line characters on the end. That's what this is doing. Then I will split that string by tabs, so that's going to give me a list of strings. Do the whole thing in a list comprehension, so I will have a list of lists of strings. And there you go. So this is the first two records. Of course, the first record is really just the header line out of that file. And then this is the first real line of data in that file. We see the participant and all this other information. Now, there's a filtering aspect to this problem, too. The investigator only cared about some of the participants, the ones that were known to have a mutation in the TP53 gene. So he presented me with a list of cases. And that was expressed like that. It's just a file that's a bunch of these. OK, so let's read that in. And when I read it in, because I knew that I was going to use this for filtering purposes, I read it straight into a set. Because if you're doing filtering based on are you in or out, the Python set type is what you should do. But just to look at the value of a set, because a set, if you ask a set to print out its elements, it'll give you the elements in a pseudo-random order. Really, it's hash order. So usually when I'm looking at a set, I will sort the set and then look at the first or last few elements. So there we go. We see the file's been read in just fine. So the first thing I want to do is I want to filter my records based on the ones that are even within the set of interest. And so I can do that using a list comprehension, and I'll go ahead and just sort it for convenience. And remember, a list comprehension like this, well, in this case, it's not a list comprehension. It's a generator expression followed by sorted, is equivalent to code that looks like that. So if you've been doing Python for a while, this is all starting to get a little boring for you. So here are the first two records. Notice by this point, I've lost my header because the header was not an actual patient that would be interesting. You know, the header line of your file is obviously not a human being with a mutation in the TP53 gene. OK. How much filtering did I do? Quite a bit. Filtered by a factor of 7. That's nice. Even at 514, that's still more than I'd want to do in my head, and the problem space is more complex than I'd want to do in Excel, so let's just plow ahead. Let's grab that header, and when I grab a header out of a file, I usually like to take the column names and normalize them, so I'll make them all lowercase. If there are any spaces, I'll turn them into underscores. So in this case, I'm just going to make them lowercase, and there you go. So here's a record. Here's the corresponding field names for that record. And if you're thinking, gosh, wouldn't it be nice if that was an object, I agree with you. So let's just create, here's a simple object type that if given a dictionary, if given a tuple of key value pairs, a list of key value pairs will give you an object and everything will behave in a nice way. So I already had one of those records. Let's just try and build one. And hey, it's working. And one of the nice things about once I've got it as an object and I'm using IPython Notebook, tab completion is working for me. So now when I'm typing my code from then on and figuring out how to do it, see how the tab key is just working. So that's pretty sweet. OK. And because I went ahead and put a repr in there, that means that the objects will print out in a reasonably nice way. I mean, yeah, OK, it's kind of ugly, but what did you expect? These record objects are fairly complex, so it's never going to look that pretty. OK, so I told you that my strategy is my outermost data type will be a dictionary, where the keys will be the composite keys I'm using to detect duplicates. The values will be the list of records. You'd like it that that list would always have just one element in there. The real world isn't like that. And I'm calling that list DB for database. Now, this is not a big data problem. You saw we were already down to 500 records at this point. If you were in a big data space where you could not fit all of your data in memory, then you're going to need to focus on just the keys. So you'd have to actually go through two passes. One pass just to find which keys had duplicates, and and just be working on that. And if your data set is even larger, you might have to start sharding out your problem space based on your keys. And remember, for this discussion, a key is a tuple of column values. But in my case, there's a fairly large window of problems that are too big for you to do in your head and are still plenty small to fit inside a computer's memory all at once. So in this case, my key is going to be the barcode of the aliquot. The aliquot is the sample. The name of the center, because if two different universities did it. Yes? It's okay. No. You said it was how many columns? 92 columns and how many rows? 550,000 and 92 rows. I would not call that big data. 92 columns. Yeah, 550. So about 500,000 rows, 500,000 rows, 92 columns is not really big data yet. You blow your RAM. If one machine can't. Well, okay, yeah. So that's the space where I'm still shopping around for a computer with more RAM or better virtual memory. I would. It is on the threshold. I mean, but another factor of 10 and you'd be there. And if you throw a couple more factors of 10, you'll be in situations where not only are you multi-pass because you're going to have to resolve keys and columns and your actual data is somewhere else and you're just deduplicating the links. And then when you're done, then you'll go back to the original data and fetch the deduplicated and filtered data. But if you go another couple powers of 10, you get in a situation where even the key space is too large to fit into memory. And then you have to start sorting your key space and sharding it out to a cluster or running it in batches. So, but if you can't do the small problem, you're not going to be able to do the big one. So let's get the small problem. Okay, so these four things are what I consider to be my composite key. The sample, the center that did it, the type of instrument, the platform on which the experiment was done, and then finally the type of experiment itself. If any of those four values changes, that's not a duplicate. That's a different experiment and we want it. But if all four values are the same, that's a duplicate. We need to resolve that duplicate. Okay, and so I was just sort of printing as it went. These are the kind of key values I'm seeing, just the keys. And at that point, my database is now shrunk all the way down to 282. Remember, I've only got, which is a strong indicator of just my level of duplicity in this data set. It's about a factor of 2. For any key, I will usually have 2 records in this case. Now, your problem space may be different. You may have a very low amount of duplicity in your data space, in which case one of the things you can do is if you were doing multi-passes through your data, your first pass would just be detecting what are the keys that had duplicates. And you could use collections counter to do that, counting the number of occurrences of observed tuples. And then after you've done that, you could focus just on the duplicates. And if something is not in the duplicate set, then those records would just pass through without any processing. So these are the kinds of keys I'm seeing. And then let's actually pull out one of the duplicates. So this is a list of records. We see one here and one here. There are 2, which is about the average duplicity we're seeing. And we're going to need to resolve that duplicate based on other bits of information, such as the published date or the reference that was used. Okay, so here's just sort of a report on the kind. For some cases, for some keys, we didn't get any duplicates at all. Others we get 2, sometimes 3. Okay, so now let's start playing with a specific object or set of objects. So here are 3 duplicates. And this is me just sort of feeling around. What am I going to have to do? And I'm really worried about that reference. Let's see, what kind of references was I getting? So I used collections. It's going to show me the number of observations and the different types of references. And I see that in this data set there were several, like about 6, I guess, different observed references. And I'm going to need to map that. Now, this was only one of several data sets I was processing. So after I was done mapping a whole bunch of these, this is the map I finally came up with. So the idea is that for anything I see like, for anything I see that looks like this, I need to turn it into something that looks like that. So you see all these different occurrences. And it's all going to simplify down to either HG18 or HG19 in this case, which stands for Human Genome Version 18, Human Genome Version 19. But the point is, I got it to something sortable. So this way, because sometimes it got really crazy. I would just not be able to sort and resolve duplicates without that. Now I've come up with a sorting function. So Python has a built-in function called sorted. Sorted takes a key function. Whenever you're doing a fancy sort, besides just doing a reverse sort, the best way to do it is using a key function. The key function says, you give me an item, and I will give you back the object that I want you to sort by. So an example of a sorting function might be, suppose I wanted to sort regardless of case. Well, my sorting function could be string.upper or string.lower. So I'm not going to change the case of the strings that I'm sorting. But when I sort, I'm going to ignore the case. And so the way to think about it is you had your original list of objects, bam, 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 and now there's this parallel list of sorting values. And Python will sort based on that parallel list of sorting values. Your original objects get pulled along for the ride, and in the end, you get something that's sorted just the way you wanted it. So here's my sorting function. It's going to be a tuple. I'm going to take my reference, and I'm going to run that through my dictionary. I'm also going to use the analysis date and the publish date. There are reasons why sometimes I need one date or the other. Basically, sometimes the analysis date was null, but the publish date was still available, and so I'll use that for breaking ties. Then once I've got my sorting function, that means that for each, at this point I can ignore the keys in my dictionary. That was just to identify duplicates and organize my data based on duplicates. Now I can just focus on the values in my dictionary. The value, remember, each value was a list of objects that were potential duplicates. What am I going to do? I'm going to sort that list and just take one end of the list. I don't need the keys anymore, just the values. So that's why I'm using iter values here. I will sort the objects in that list using my key function. Then I will grab the last element. I'm done. Append that to my final list. Boom. And if you wanted to do list comprehensions, here's the equivalent. Those two are identical. We can look at one of these records that we got out. And so this is the data that I want to start writing back out. So I did do a final thing while I was still building this interactively. I did a final error check and eventually got this to none. Now I have to decide what my output format's going to be, what are the order of the fields I want. So this is me doing it. By the way, whenever you want to create a list of strings, it's generally better to, it's very tedious to go square bracket, quote, string, close quote, comma, quote. It's very, very tedious. So usually what I will do is I will just create a string. As long as the things I wanted were all one word each, no spaces inside my elements, I could just take a string, separate it by spaces or new lines, and then split it. And I get my list out. So this list of fields is what is going to drive my output. And then all that's left is to go through a quick little loop and push it out. So there you go. And I'm using getAttr. When you want to extract data out of a Python object, but you want to do so not using dot notation, but in more of a dictionary style, where I've got a string that is the name of the value I want to pull out. That's what the built-in getAttr function of Python will give me. And there you go. Now I've written that file out. And this was called a work list because this would be handled to downstream automation to actually extract those BAMs from CG Hub and do the first round of processing for each. And I can show you what that looks like. Just like that. But now, whereas the original one did have duplicates all over the place, this one does not have any duplicates. If I sort this, I'm never going to see, well, I will see duplicates of an aliquot barcode, but only if there were two truly different experiments that were performed. And I guess I was going a little bit fast because I'm finishing 3.5 minutes sooner than I thought I would, but we can just start going into questions now. So, yo.
Was your professor impressed with this turnaround time? Was this a one-day project?
What's that? Yeah, OK. So the question was whether or not the professor was impressed that it was a one-day project. This actually, because of meetings we had to even figure out what his problem space was, and I had to do a number of rounds. It's like, well, if you see two things that look like this, what do you want? That, and also I was requiring that during this exercise, my team shouldn't have even had to do this. It was another team, the cancer analysis team, that should have been having to do this work. My team got drafted because we had the relationship to the Cancer Genomics Hub and the programming skills to successfully execute this. So I forced that an analyst on the cancer analysis team would be present when all of this was going on. And so between meetings with the professor and requiring that she would be present and learning from this exercise so that I would never have to do this again, that's what stretched it out to 2 weeks because we had to make our, mostly because we had to make our schedules line up. It was, if we'd done it all at once, like very efficiently, this whole thing with experiments and false dead ends would probably have been like about a day. I might have pushed it to an afternoon. But at the end, it was a win because the professor got what he needed, and the lady in our cancer analysis team then requested all of our scripts so that she would be able to do something like this next time, and I won't have to deal with this again. IPython is an excellent teaching tool. IPython closes the loop between how do I solve this problem and how do I teach a coworker how to solve this problem. Did you have a question? Yes, if you wanted to report on the duplicates, you would have used the same. So the question is, what if we wanted to report on duplicates? You've got an occurrence where 5 records have occurred that are duplicates. And yes, I want the deduplicated unique record at the end. But I also want to report on my duplicates. How would I do that? And this is mostly useful if you have a data set that's got what I would call low duplicity. So there are most of your data is unique records, but you've got a few clusters of duplicates. OK. Anyway, reporting on duplicates is really a case of going back to that outermost dictionary. Remember, and the values in that dictionary were lists of records. And then finding those values, those lists, that had more than one element and focusing on that and saying, all right, and maybe even focusing on the ones that had the most numbers. Like, what was the biggest source of duplicates? I would take the values out of my dictionary. I'd go db.values and then sort that. Well, actually, and sort it, but where my sorting function was the len built in. So now I would have a list of lists of duplicate records that were sorted by the length of the list. And I go to the first element in that outermost thing. And that would be my biggest cluster of duplicates. And I would take that list of my biggest cluster of duplicates and start diagnosing what were those duplicates coming from. So the way I would do that in the notebook is, remember, I still have this DB, so I'd go db.items. That's going to give me a big, long list of lists. But I could then sorted and that's going to give me, again, a list of lists. But now if I just grab the first, well, just grab the first one. And that is my biggest or tied for biggest cluster of duplicates. And so you'll notice that these all have the same aliquot barcode. I never had more than 3 duplicates in this data set for that particular cancer type. There may have been other cancer types where I had larger clusters of duplicates. So in your case, if you've got like one URL can produce many duplicates and you wanted to like get in and figure out why, this is what I would do, is I would use that approach, sorting by length of list, find my biggest cluster of duplicates, and then start drilling in. And I would expect that, if I had a URL field in my thing, then they'd all have the same URL. So now I'd go, well, what was the URL for the first one? So in my case, it was, say, aliquot barcode, but so I'll use that as my proxy for your URL. So here, I'll grab just the first object. And then I will grab the first element of that, and that might have been your URL, like so. Just drill it down. And so that would say, this is the URL. Or in my case, it was the aliquot barcode. But in your case, it would have been the URL that gave me either the biggest cluster of duplicates or tied for the biggest cluster of duplicates. Now go troubleshoot that. Did that answer it? OK. Any other questions? Yes?
Have you ever tried using Pandas? I know there's deduplication stuff there, but I don't know if it's as sophisticated as.
OK, I have not used Pandas for deduplication. I have used Pandas for other things, and I love Pandas. If you're doing anything that's more statistical or time series-ish, or you're needing to do aggregation, you should be using Pandas. So, and Pandas works perfectly well with IPython. So there you go, Pandas. Thumbs up. Anything else? OK, well, it's not like we're paid to use up the whole hour. You guys can go out and have more breaks.